Which glasses have actually better display panel? And how does real measurement data say about those panels? This is AR Tech Insight. I'm Dr. Liu. Welcome to episode 17 of our expert talks. And this episode, I invited the former Apple display expert, Dr. Radu Reit, to give us a talk. He breaks down the display and optics of those smart glasses. Hope you'll find this helpful.
Any display device that an Apple device may have today, and maybe a few that will come out soon, I hope, to make all of that time worth it. But more recently, I started the Display Training Center, which is essentially a way to practically educate people about what we need to do as a display manufacturing industry to really solve fundamental product engineering problems. And when I say fundamental problems, I don't mean just, how do we get a denser transistor density? How do we get a brighter OLED emission? It is significantly more complicated than that. And it is a multidimensional problem that involves cost, involves manufacturing challenges, and of course, new technology introduction. And that is what essentially Display Training Center was founded to do for experts in our field. But like I said, I want to baseline us. We always talk about AR glasses, and today we're obviously going to talk about them at length. But augmented reality glasses are way too broad of a category. I think we define them in such loose ways that the AR meaning truly starts to lose the initial meaning that everybody tried to talk about when we talked about augmenting reality. But really, today I see AR glasses falling into three main categories. Number one, we have display glasses. A display glass is something like an Xreal or a Viture glass, where essentially we just have an external monitor. These types of glasses are very visually excellent display systems. They typically use microLED panels that we'll talk a little bit about later, but they're a tethered device. You tether to your compute puck, whether it's your smartphone or your laptop, and you are just projecting that information. We're evolving past that, certainly. Xreal especially is pushing the boundaries on what we can do with these categories. But at the end of the day, you are not necessarily digitally overlaying information on top of the physical world. You are just seeing, a digital screen very near to your eye. I can kind of make this equal to a portable virtual reality system. The other more close to, but not quite augmented reality are what I'll refer to as HUD glasses or heads-up display glasses. These are untethered. They're kind of what you see here, the even realities that I'm wearing right now. And they certainly provide some visual feedback, some information about what they are doing themselves or what your compute device, whether it's a smartphone or some other connected device, is doing. But essentially, they're just providing that information to your eyes. There's no necessarily overlaying of that information with what you see in the physical world. It is hey, here's a notification. You've received your text. You've received your email. You should probably go into your actual compute device and check out what that's about. This has been a very robust category recently because of the massive focus on artificial intelligence applications. And very soon I'll be putting out a video on these even realities. I think we are starting to see the killer application for these types of HUD glasses with the transcription or conversational awareness, the translation features, all of these types of heads-up display applications that don't require digital overlay on the physical world and just require some minimalist level of display delivered directly to your eye is a very, very interesting product category. But the last one that we'll talk about is true AR, true augmented reality. This is complex. I show a picture here of the Snapchat spectacles, and frankly speaking, this is a category that's still very early on. You may have a HoloLens device or a Magic Leap device that is actually putting digital information co-located with the physical structures that are in front of you. But this is very complicated. It's very computationally intensive. It requires, significant compute, like the simultaneous localization and mapping algorithms, the SLAM algorithms that really take a lot of effort, take a lot of power, and take a lot of space in terms of a hardware envelope. So these true AR glasses are certainly a category that exists, but I would say the two on the left, our display glasses and our HUD glasses, are really what's making big waves in the consumer space today. Now, when I talk about user experience for these glasses, I really see maybe a concerning trend about what brands are advertising versus what we really care about. And I get it. I come from a technical field. I was in engineering for all my career. It's very easy to set, the display PPI. I now have 3,000 pixels per inch. I have 4,000 pixels per inch. This is so easy to say I have a bigger number than my competitor, or I have a bigger number than the previous generation. But from a perspective of a user, is that really the most important thing? I would argue that probably not. We need to convolve these types of hard specifications that everyone latches onto in terms of PPI, brightness, camera resolution, chipset, etc., with something else, with a user-targeted critical to quality metric to give us something that users actually care about. So how do we get from PPI to, well, how good is the image? How do we get from brightness to, am I going to be able to wear these devices all day long without having to recharge? And so on and so forth. There's a missing component here. And I hope that with all of these teardowns that DTC is doing, we can eventually get here. We can start digging into the specific hardware choices that have been made by big brands and manufacturers and talk about what's gone right, but maybe what's still leaving some room for improvement. And so, we got to come back to the money aspect of things. Why do we even focus on the display and optics in the first place, right? The eyewear has a whole host of other compute and housing and memory and other issues, other components that have to be further micronized to be able to make this type of device. But I would say that display and optics are really the entire device. Counterpoint put in an interesting article, an analysis of the Xreal 1 late last year, where they break down the entire bill of materials of the device. And if you take a look at what this actually means from a total cost of components, the display from Sony in this case, and the optics that Xreal designs and sort of manufactures themselves, they make up nearly 70% of the bill of materials. Essentially, the device you're purchasing, yes, there's a Snapdragon AR chip inside. Yes, there's some Micron memory inside. But the primary cost that's driving what you pay at the end of the day is going to be based on the display and the optical solution that was chosen for that particular device. Something we'll also go into a little bit later is that the majority of the weight, really one of the key metrics for how comfortable these devices are going to be for wearing the entire day, is going to be front loaded by these display and optics components. The display itself is generally a low weight contributor to the overall system, less than a gram in most cases, but the optical solution tends to be much bulkier. And we'll take a look a little bit later when we go into the diffractive or geometric or birdbath optics that are used. But generally, this is ultimately about 25% or a quarter of the overall weight of your device, purely due to the optical solution. So it's even worse in VR. We won't talk about that necessarily today, but display and optics drives the price, drives the comfort, and ultimately drives why we're putting these things on our head in the first place, that there is an image quality that gives us sufficiently useful information when we need it. And I would say that not only do we have to do this analysis on paper, we have to actually tear the device down and start digging into the hardware that is used. A big brand, in this case like Future, is going to be very optimistic about what they talk about. They're going to advertise everything about their display choice as well as they possibly could, and they're going to tell us how many nits are going to be delivered to your eye. And we should trust, but we should verify. And not only verify, we should also try to understand what are the other issues that come along with the choices that they've made. On paper, we may have a fantastic OLED display, but because of certain design choices, in this case, Viture's diopter adjustment mechanism, not only have we had a very interesting adjustment mechanism added to our device, we've actually had significant weight added to the unit. If you take a look and do the measurements yourself, you can see the micro LED panel, excuse me, the micro OLED panel is about 0.5 gram. But because of all of the extra magnesium alloy casting elements that we have, the linear screw elements that were added, the extra flex to extend the connection from the OLED panel to the main logic board, we've added more than almost 4 times that amount of weight per eye to actually get this type of mechanism in place. It had a lot of volume, a lot of bulk, which further reduces comfort and all-day wearability for the user. And in this case, it's not as big of a driver, but we increase cost. Every single new component is going to make this more expensive. And we won't talk about the specifics of how much Viture paid for these micro OLED panels, but they're adding more dollars each time they cast these magnesium alloy plates for this diopter adjustment mechanism. So this is why we tear down. But I think this is a good time to go into the specifics, what maybe this audience really cares about, and that is displays and optics. And I wanted to start today with displays because it's very easy to imagine. We really have 3 main options that we're seeing on the market today, certainly, but also in competition with each other for market share, but also for technological superiority. And at the very top, I have an example image from one of my teardowns where I see Jaybird Display's Hummingbird display, the micro LED, VGA monochrome green panel that is essentially now a staple in any device that uses this type of technology. In the middle, you have the very stereotypical Sony panel, a Sony micro OLED display that is now ubiquitous in the industry for anybody trying to use micro OLED screens, typically for bird bath optics. And then in the bottom, I would say we really only have one competitor here in the LCOS space, Meta, with their Meta Ray-Ban displays. But you'll see, and hopefully after the comparison of all 3 of these technologies, we really have an interesting head-to-head competition between these 3 displays. They all come with really impressive pros, but not completely ignorable cons that will have to make this a very tough decision for the product designers. I wanted to start with maybe micro OLED because essentially this is the best display, in my opinion, on the market today. If you essentially want to take your OLED screen, whether it's your OLED TV or your smartphone OLED screen, and get that same image quality, the same brightness stability, the same color uniformity, a very large color volume in your heads-up display, you're going to be choosing micro OLED. If you can deal with the limited brightness of these devices. Generally, the OLED structure is very limited, and we'll talk a little bit about that. But these are incredibly uniform displays and have phenomenal picture quality for any application that they make sense in. Again, this comes back to the type of processing that's done for these devices. Generally, we're working with a structure known as WOLED or white OLED, where we deposit an OLED layer onto our wafer and then individually filter out the red, green, and blue channels that we have using this color filter mechanism. You can see in the top right there an image from Sony. They've published papers in the Journal of Society of Information Display where they talk about exactly how they do this color extraction using their color filter technology and how they can improve brightness in certain cases, but really we're pretty limited in terms of maximum brightness that we can get out of these. I like this image in the bottom right. This is a direct image from one of the, I believe, Xreal panels, where we see the individual red, green, and blue hexagonal subpixels that we turn on to make, for example, a white background in our OLED panels. I think it's important to know we really like OLED at DTC and generally as an industry because OLED emitters themselves are getting to be really, really pure. Ray Neo actually has started using SIA panels, SIA mainland micro OLED supplier that is really taking a chance on some new OLED emitting technologies. And that chance is seeming to pay off because we're getting very, very pure red, green, and blue primary emitters that help us cover a very large color space as well. And so, what we're looking on the right here is the individual emission of the blue, green, and red subpixels, and the full width half max, or how wide this peak is at roughly 50% intensity, really determines just how good our picture quality is. And I would say anything under 30 nanometers is fantastic. And anything under 40 is very good. So we can see that all three of the primary emitters here are excellent for SIA. But it's important to know, not all OLEDs are made the same. And actually, what the majority of people are using in the industry today are the Sony panels that we see in the Inmo Airs, in Xreal, even in Viture, actually, as I pointed out earlier. These Sony panels, because of their more mature manufacturing process flow, they are slightly lower purity emitters. If you take a look at just the green curve in the very bottom, the full width half max, how wide that green peak is almost 70 nanometers. This, from a visual quality perspective, means that we just can't make as many colors as we can with the top OLED device. And it gives us a overall maybe less saturated image. Again, may not matter much for people, but certainly as we get into heated competition between the visual capability of all of these displays, I'll take the display on the top over the one on the bottom any day.
Sorry to interrupt.
So, yeah, go ahead.
This is very interesting. This figure, the comparison is very, visible impact, and that's, you can see the quite difference, right? So the above one is the Xia, I believe, right? Is a Chinese.
That's right.
This OLED panel, and the bottom is the Sony, right? Which is the standard, like before it's kind of standard. So from this figure, does that indicate that Xia is doing better than this Sony panel?
From a pure color volume or color space coverage, the answer is yes, right? Xia panels can absolutely cover a larger color space. They can reproduce more pure reds, more pure greens, and any color in between than Sony can. But that's not necessarily the entire story, because power consumption also comes into play.
Yes.
So it's a complicated story, but I would say from just a color and visual quality, when I look at the display, I want to look at the top one more than the bottom one.
Okay, so now when you actually look at those kind of the panels, so the top one is, you can visibly see better, right? Better than the bottom.
Yeah. You will be able to see HDR content, for example, in the top panel. The bottom panel likely won't be able to produce, Dolby HDR content because of the brightness as well, but definitely because of the limited color space that you can reproduce with this emitter stack.
Yeah. All right. Okay. Thank you. This is a very good result of this image. Okay, thank you.
Yeah.
You can continue.
Sure. And we'll get to more questions maybe towards the end, but long story short, yes, the OLED layers, the transport layers, the emission layers are ultimately what are going to be able to drive this purity of color. And the fact that SIA uses a tandem architecture, which is something that's a little bit more complex than we have time to get into today. So why don't we always use OLED? If OLED's so good, if I'm always talking about how amazing OLED looks, why not always use it? It is brightness. Brightness is significantly limited for OLED. Kind of the industry standard has been set at about 10,000 nits, or 10,000 candela per meter squared. In the top right, you see one of Sony's newest 1080p panels they've launched on the market. And that is, again, at 100% duty, so 100% on, they can reach up to 10,000 nits. In comparison, a micro LED panel can get up to 10 million nits, monochrome green, so not a fully fair comparison. But even when we have full color micro LED, we can get up to 1,000 times brighter, fundamentally because of the inorganic nature of the light emitting diode that we're using, rather than the organic structures in the top right. And so that's number one. Number two is that even for equivalent brightnesses, the power consumption is significantly higher for micro OLED. If we're looking for all-day wearability for a device like a smart glass, micro OLED is just frankly not there. Not only are we not bright enough for some of the optical architectures that we'll talk about later, but we consume so much power. Now, I want to give an example that is a little bit empirical, but it's still useful for this audience. If we take a look at the micro OLED power consumption, even if we have displays off, the Xreal Air 1s consume about 1 watt of power, about 900 milliwatts. We turn the display on at minimum brightness, so this would be almost invisible in a very lighted environment. We are drawing 1150 milliwatts. So about 250 milliwatts of power consumption just for the single one micro OLED panel alone at the lowest brightness setting. And as we turn that brightness all the way up, to the 5,000 nits that micro OLED, that particular OLED panel is capable of, we're consuming an extra 750 milliwatts to give us 5,000 nits. In comparison, the Rokid glasses, which use a single monochrome green micro LED panel, full power consumption for the entire device with the display on at maximum brightness is 350 milliwatts. This is, almost an order of magnitude lower power consumption for the entire device at even much brighter overall device capability. And this is
this
where
is also
micro
really
OLED.
interesting.
This is where micro OLED starts
because
losing.
So we have seen a lot of this kind of comparison, but I've never seen such kind of like detailed this very accurate numbers. So for the display off, why is still consumes like almost 1 watt for Xreal?
Yeah.
What happened?
So I'll give Xreal some defense here. This is their very first product. The Xreal Air 1 was, you may be familiar with when Xreal was called Nreal.
Yes.
This particular product started drawing a lot of power even with the displays off, just for some onboard processing. I definitely don't think that this is an optimized PCB design. There's probably some buffer across every single module, across the display, across audio, across memory, which actually there's no memory in this first one. But there's a lot of buffer that was built into the first product, which means that we had a very high off display power consumption. What I think is really important to look at is the display off versus display on power consumption. And so it's important to remember for these types of glasses, you tend to have 2 displays, right? Not 1. So not only are we getting 750 milliwatts of extra power consumption for 1 micro OLED, you need 2. That's another 1.5 watts of power draw to just put the 2 displays onto your eye. Yeah, Rokid has a really interesting structure. We could talk about it later, but essentially this 350 milliwatts is for both eyes. And, we can get to that later. Okay, so now I talked about how inefficient micro OLED is. Let's talk about why micro LEDs may be a little bit challenged as well. We already covered, these are very power efficient devices, but there's a lot of manufacturing challenges that will make micro LED displays a challenge for integration, whether it's from cost, but also from actual technical issues. We already know, we don't have to get into the specifics, but the inorganic LED structures that we are familiar with in micro LED just means that we have much more efficient light extraction, a much higher EQE, external quantum efficiency, of the light that's being extracted out of these panels compared to our micro OLEDs. But the color purity actually, one question I get a lot is, well, OLED is, an organic emitter, an inorganic light emitting diode should be a much purer color, right? And the answer is no, actually. I show here an example comparison between Rokid glass, the monochrome green micro LED, and Rayneo's green micro OLED subpixel. And in both cases, we have around 30 nanometers full width half max for these emission. The peaks may be centered slightly differently based on the specific device, but at the end of the day, we are seeing a roughly similarly pure emission from both micro LED and micro OLED. So don't take it for granted that micro LED necessarily means a pure color. And not only does it mean does it not necessarily mean purer color? I would argue it actually provides a much worse manufacturing tolerance, which turns into a much worse visual quality sometimes. MicroLEDs are notoriously bad in terms of uniformity across the entire wafer. I show here a direct capture from my Rokid glasses microLED panel, where I extract the device and I start zooming in at various brightness levels into the individual pixels. And you can start seeing what is a solid green line in this slider bar. Actually, if you look further and further into this, there is massive brightness non-uniformity from adjacent pixels. In the far right, you can see blue arrows that point to individual pixels that are being shown, where brightness non-uniformity can be 100% or more between adjacent pixels, meaning that one pixel may be twice or 3 times as bright as its nearest neighbor. This is a big problem, and it's less noticeable in devices like this monochrome green display that we have, especially when brightnesses are quite high. But as we progress this industry to a full color solution that is truly competitive to the micro OLED devices, we are going to have significant challenges for micro LED displays. And the last display architecture that we'll talk about is LCOS. There's only one person in the industry right now, or one corporation in the industry that's really pushing this aggressively to consumers. That's, of course, Meta. LCOS is an interesting beast. I was not very pro LCOS until this particular device came out. But when you actually take measurements, this device has very good power efficiency on the scale of micro LED, in fact. It's also leveraging a much more mature manufacturing supply chain. LCOS has been around for 30 plus years, and the LEDs that are being used to illuminate the LCOS panel are themselves very mature as well. Again, 30 plus years for blue and even longer for red and green. But with LCOS, we do have new optical artifacts that we have to be worried about. LCOS itself, liquid crystal on silicon, is just a fundamentally different way of producing an image to the user. Whereas micro OLED and micro LED panels are directly emitting the red, green, and blue subpixels to the user's eye, the LCOS panel is a reflective technology. And so you take a blue, green, and red source, that we see in the far right, and you are strobing these sources. So one after the other, and reflecting them off of this liquid crystal on silicon panel to deliver individual red, green, and blue frames. And what you hope for is that you do this often enough that the eye and the ocular nerve essentially reconstructs the full color image off of these time-delayed red, green, and blue individual channels. But the truth of the matter is that it doesn't quite work that well. You will be able to see the time difference between these frames in certain situations. The color purity itself is excellent because the input LEDs are themselves very excellent in terms of color purity. But as I talked about, what you're really looking for is that time delay between the individual blue, green, and red channels. We take the Meta Ray-Ban displays here, and we actually move the head, in this case, in various directions in X, Y, and capture this with 120 frames per second camera capture rate. You can already see at 120 frames per second that we're starting to see blue, green, and red channels separating as they get delivered to the camera sensor. And you can imagine that the camera sensor itself is your eye. It is receiving at 120 hertz these spatial frequencies at a different location. And this is essentially what you see with any LCOS-based display, that if you are going to move your head very quickly, you're going to separate those colors. There's a couple of ways to fix this. Carl and I talk about this a little bit in our Meta Ray-Ban display technical deep dive. You can go much faster field rates. You can use some additional computational processing to try and get to frame render something that is different than what was intended to match the inertial movement of the head. But at the end of the day, it's fundamental how this technology works. You are just separating these channels instead of emitting them all at the same time. And it's a problem that is going to be really difficult to solve. So this is where we get to a holistic display comparison. And we talked about 4 key consumer critical quality metrics: visual clarity, battery life, comfort, usefulness. But I want to add here, and towards the end, cost. Because at the end of the day, you can have the perfect display with the perfect optical solution, but if you can't make it for cheap enough, you're never going to be able to sell hundreds of millions, if not billions of units over the course of the product lifetime. And so this is where micro OLED in the far left column really has a challenge. It is currently some of the most expensive technology on the market. Again, because it's very high visual quality, there's certainly applications for this. And so the excellent visual clarity allows us to make things like these types of lightweight VR headsets or display glasses that I've talked about. But micro OLED is fundamentally limited by the fact that we have minimal brightness. And so that's going to kill battery life, as you have to draw more and more power to increase the brightness of your device. And these are generally paired with very bulky optics. We'll talk about birdbath optics later, which are very heavy, very volume intensive, and make for an overall lower comfort device. MicroLED is kind of the nice middle here, where the cost is lower, certainly than micro OLED, but it's still not low enough. We're not using the same economies of scale that we have for commercial LED packages yet for micro LED, and so the cost is still very high compared to other microdisplay technologies. The visual clarity is okay, especially for monochrome applications. But as we saw earlier, there is some non-uniformity that's going to really be challenging for micro LED to solve without really sacrificing some of the other gains that they make in battery life and overall comfort, because these devices are so small and are able to be integrated into very comfortable form factors. LCOS is, I would say, an unlikely winner, at least in my opinion, because it's not only the lowest cost, but it has a great visual clarity if you can get away from this color breakup, field sequential color breakup that we just talked about. This asterisk is a big asterisk. There are some brands who are just not going to accept that, if I turn my head to the left and turn my head to the right very quickly, you may see a very poor image because of the separation of the individual colors. But if you can accept that, which it seems like Meta was able to for the Meta Ray-Ban displays, then you still get great battery life for the display. You still get a very comfortable overall device, and you can finally make a full color heads-up display, or maybe even augmented reality display like the spectacles. So everybody's got challenges, and you're just going to have to choose what specific display technology to build your device against based on what you really want. Do you want low cost and high performance? You're probably going to go with low LCOS. But if you want the best possible image quality, you're going to be making a display glass like Xreal and Rokid. Okay, so the last half of the talk is going to be on optics. And I think this is very interesting because there's just so much innovation happening here, especially in the 2 primary optics that pair with all of the display technologies that we just talked about. Number 1, birdbath, which is a polarization control reflective technology, and our waveguide technology, which covers both a reflective and a diffractive element. We'll start with birdbath because I think this is probably a very interesting topic for most people who have used these types of display glasses like the Xreals. Essentially, what a birdbath optic is doing is it's controlling the polarization of your generally unpolarized emitted light, whether it's a micro OLED display, but this doesn't have to be micro OLED. It can be LED or even LCOS. And it controls that polarized image as it travels down through lensing elements and bounces off of other optical elements. You can take a look later on the blog at displaytrainingcenter.com. There are specific diagrams of how the polarized light interacts with each individual element in the birdbath optics. But essentially, you are bouncing this to increase the focal distance of the image, but also then project the image at 90 degrees relative to the original display panel. What this causes us to do, though, is to lose a lot of light. This is a very lossy element, not as lossy as a diffractive optic, but we'll get there, where, more than 80% of the light is generally lost throughout your birdbath element. There's one example here that I show, I believe this is the Xreal element, where you start with a 5,000 nit panel, but already you have to start linearly polarizing your outgoing display light. So you're going to cut your maximum emission by more than half to around 2,300 nits. You're then going to go and bounce off of reflective polarizer first, and then bounce off of the half mirror, which again reflects maximum 50% of your light. So we're already down to, this shows 1175 here. And then the reflective polarizer, even though we are in the correct polarization state, we're only 90% efficient in most cases. So at the end of the day, you're going to have around 1,000 nits delivered to the eye, absolute maximum. And realistically, it's going to be even lower than this. There's other absorption, other reflections that I haven't accounted for here that are going to continue to lower this maximum brightness. Again,
these values are, sorry to interrupt, these values are based on measurement, right? It looks like.
Correct. These are empirical measurements of the transmission through each of these particular elements.
Yeah, it's roughly like 20%
of the original light. Yeah. So, it's in defense of the big brands, they are advertising correct values. If somebody told me that we have a 5,000 nit display that's being delivered to my eye, I would immediately call BS, because there's no way to get that with any birdbath optic using an OLED panel today. So the birdbath optic is relatively lossy, maybe 20% or less of the light delivered to the user's eye, but it's also not really going to allow you to see the world, right? If we talk about AR glasses as allowing us to digitally overlay the information, you are actually not going to be able to do that with these glasses unless there's some sort of camera pass-through. And that's because you just have very little transmission through the glasses to begin with. If we do the same exercise, but now for light coming from the world going through the birdbath optic, we actually have an even worse transmission. If we take a look at a lens element like what maybe Viture is using here on the outside, roughly a 30% transmission to start off with through an off-state electrochromic element. Then we take that 50% half mirror transmission and another 50% reflective polarizer transmission because we have unpolarized light coming from the world. Even when we forget about the transmission of other losses, which we cannot because there's going to be other issues. But if we give the best possible chance, only about 8% of the light is coming in from the outside delivered to your eye directly. Again, very, very low transmission of the world light. And it means that you're not really going to be able to see what's happening outside while you're using these types of glasses. These are for static environments, and that's why we call these maybe lightweight virtual reality glasses. When we move away from this lightweight VR side, we get into waveguides. This is, I think, maybe what some of the folks in the audience are most interested in. What are the waveguides that allow us to, avoid some of the challenges that birdbaths present and give us a really good image quality, but still being able to see in front of us while we use these glasses? And that kind of falls into two separate categories. One is a reflective waveguide or a geometric waveguide, like the Ray-Ban Metas use from Loomis. And two is a diffractive waveguide that uses a fundamentally different way of rerouting the light. We'll talk about that later. But this is, a wild west of manufacturers today. I'm sure you've had previous talks on this, and it's a very interesting space to play in. We'll start maybe with the reflective or geometric waveguides. There's only a handful of companies that really work on this, but essentially what we're doing is we're using either full mirrors in the case of the input pupil, where the image is injected into the waveguide. You generally have a complete mirror to bounce the display light into your waveguide, or partial mirrors that help extract that light away from the internal reflection that's happening within the waveguide and out to the user's eye. These are very, very efficient because we're using mirrors, even when we have to use partially reflective mirrors, right, that generally let a lot of light through and only extract it a little bit. You can get very good efficiencies for these types of waveguides. For one-dimensional waveguides, like the one that we saw on top for the InMO Airs, you can get in excess of 10,000 nits per input lumen of waveguide efficiency. And even for two-dimensional ones, like the ones that we see here, where we have to expand the image first, if you follow the laser input source down and to the left, that is an image expansion and then a reflection to the actual exit pupil. These are still more than 3,000 nits per lumen in terms of an overall image efficiency. So reflective waveguides are great, but they also add a lot of heft. We take a look at these types of waveguides. All of these optics are generally 15 to 20% of the entire unit weight. Imagine that you get quoted that InMO or Radio or somebody else is making an 80 or 90 gram device. 20% of that is now going to be in the waveguide. And this is very consistent across all brands, all types of display and optics combinations, that the majority of the heft of your device is going to be sitting directly on your nose and on your nose for the entire day, and can get very, very uncomfortable. It is going to be the most challenging part of this to solve, but it's certainly something that no one manufacturer has been able to solve yet. And for reference, even the birdbath optics in the far right from the Churs are kind of around the same total weight percentage. Around 20% of the entire unit weight is concentrated on your nose bridge in the form of that birdbath optic. And the diffractive side, the story is slightly different from a technical perspective. Instead of using mirrors to reflect the light, we're using nanoscale gratings to diffract the light. And I won't get into the specifics of diffraction here, otherwise we need a few more hours. But essentially, we're using the first order light diffraction from an input source to reroute the image through the waveguide to other diffractive elements that will further extract that light to the user's eye. We can again do a one or two-dimensional diffraction, similar to how we did reflection, where we may have an expansion, a very clear expansion grating, like the Rokid one in the very bottom here. But the concept is very similar for both of these. And this is unfortunately a much easier to manufacture device, but it is a much less efficient device. All manufacturers so far are quoting around 1,000 nits per lumen or less for their overall efficiency. Now, to end us on some minor technical comparison, I would say these types of waveguides are even more noticeable from a device impact, because the devices tend to be smaller. If we look at these types of devices versus the reflective waveguide devices, these devices are generally lighter. Again, that's why we are buying these devices with diffractive waveguides in general, because we've been able to slim them down. But now the waveguide itself is an even bigger component of the overall device, and an even bigger consideration that needs to be made for whether or not we have a truly comfortable waveguide. So I'll end the optics comparison after just a short little description there. There's three main optics that we look at. The birdbath, which is more for that lightweight VR application. Tiana, you might be unmuted. All right. So we have three separate main optics for all of our devices, which is the birdbath and then the geometric and diffractive waveguides. Really, this isn't a choice that you make when you are creating a product based off of which one of these three do I make for my product. You have to select what your product is intended to do. Because if you're going to make a lightweight VR or a display glass, there's no reason to pay the premium for a geometric or a diffractive waveguide. The bird bath itself, which is a very low cost solution, is going to give you the best image clarity when paired with a micro OLED panel. And so your optics device is not a variable that you choose during your device creation. It is a resultant variable based off of what device you try to make. So if you're making a lightweight VR, you're going to choose a bird bath. If you're making a heads-up display, this is where you can start choosing between a geometric or a diffractive waveguide based off of what is most important to the user. Is it battery life and visual quality? Then you will have to pay a premium for a geometric waveguide. But if you're okay with the slightly lower visual clarity of a diffractive waveguide and higher power consumption, then you can start paying a little bit less for a diffractive waveguide, but maybe not as great of an end user device from a visual quality perspective. So that was a very high level overview of this display technology with maybe a little bit of data that you have not seen from these brands. And I think the three main things that everyone should take away from today is that we have a lot of options, right? We have three different display technologies, really even more than three optics technologies, but there's no one size fits all solution to the augmented reality headset industry. You have to do a very individual and tailored solution depending on the specific product that you want to build. And really, the winner in this industry is not going to win based off of the technical metrics or just how great of a display quality that they can make. They're going to be making something very cheap. And they're going to be making something very cheap at a good enough quality to make sure that we can enable really high volume applications. And those applications, unfortunately, are not going to be driven by the hardware teams that we may have in this room. It's going to be software applications that we just don't even know are being created today. So hopefully, the software guys can make something really impressive for us so we can sell more hardware. And if there's one upside, is that there's a lot of innovation still to be had. We didn't quite see every single one of these combos. There's 3 display technologies and 3 optics technologies, so you'd think there's 9 total combinations. Well, we've only really seen about 3 or 4 combinations. But some of those other ones that we haven't seen are being worked on today, and I think will give us some really unique advantages in the future. So with that, I'd like to thank everybody for their time on a Sunday morning or a Saturday evening here in the US, or a very weird time in Europe. You can find me online at Display Training Center, either on displaytrainingcenter.com or on YouTube and Patreon. And then for anyone attending the International Conference of Display Technology, ICDT, this year in Chongqing at the end of March, early April, I have been able to discuss with the conference organizers that we can provide you a discount for this. Unfortunately, the way to get your 300 RMB discount is going to be by emailing me directly at info@displaytrainingcenter.com with your name and registration email so that we can provide you a unique discount code. But I hope to see you there, and thank you again for listening.